All right, welcome back. As you know, we did 4.6 before we did 4.5 because I wanted to finish up all the different possible ways to prove triangles were congruent before we moved on. What we are doing today is something called the isosceles triangle theorem, also known as the base angles theorem. So the base angles theorem, THM, which is sometimes called the isosceles triangle theorem. Take either one. Okay, so it says the following are all examples of isosceles triangles. How would you define an isosceles triangle? So if you're looking at all these things, what do they all have in common? Well, you should notice that that side is congruent to that, those ones are congruent, and these ones are congruent. So an isosceles triangle is going to be, here's your definition, isosceles triangle, a triangle with it's funny, with exactly two congruent sides, not three, two. So here's an example of an isosceles triangle. What we are going to do is look at its anatomy. We know that this side and this side are called the legs. Down here is called the base. So the legs are going to be your two congruent sides. The base is the side that is not congruent to the other ones. These ones right here are called the base angles. Up there is called your vertex angle. And those are all the parts of an isosceles triangle. So if I'm talking about the vertex angle, you need to know the vertex angle is going to be the one between the two congruent sides. If I say the base is the side that is not congruent to anything else, and the base angles, as you can see, are right here. So what in the world does the isosceles triangle theorem say? It says if two sides of a triangle are congruent, then the angles opposite the sides are congruent. So here is what the actual theorem says. If those are congruent, then those are congruent. Now, we have been doing proofs just to do proofs, just to practice proofs. Why do we actually learn proofs? We actually learn proofs so that we can prove things are true. For example, this. I want to try to figure out, I'm going to use logic to make sure that this is actually true. So how I could go over and do this is if we have these being congruent, well, all the proofs we've been doing so far have had two triangles. So what I can do is I can go over and drop this down, and that's a right angle. And I could go over and show that now these angles must be congruent. So how am I going to do that? Well, we have the reflexive property. We have it is given that these sides are congruent, and I drop this down so it intersects at a right angle. So we know these two triangles must be congruent by HL. If these triangles are congruent by HL, then we know that the two angles are also going to be congruent. So those angles must be congruent. Now, let's go ahead and look at some applications here. If we know that that is congruent to that, then we can go over and set them equal to one another. How did I know that they are congruent? Because if those sides are congruent, then those angles are congruent. So we would end up having 2x equals 90, and you end up getting x equals 45. All right. Now, if this thing is a square, we know all the sides of a square are congruent. Now, looking at this triangle up here, opposite sides of those congruent sides must be congruent. Those angles, the base angles theorem or isosceles triangle theorem says that. So we know 4x plus 2 equals 3x plus 18. And we could solve. 3x minus 3x, you get x equals minus 2, and you get 16. So x equals 16. Now this one is just a little bit trickier. We know that this angle is going to be congruent to that angle because they are opposite those congruent sides, but I don't even know what this one is. So how could I do this? Well, one way you can do this is you know that this is 40 degrees, so that means you have how many degrees left over? 180 minus 40 gives you 140. They must be evenly split between these two. So if it's 140 altogether, then this one must be 70 and this one must be 70. So we can now say 11x minus 18 equals 70. If I add 18 to both sides, you get 11x equals 88 and x equals 8. And there you go. Now the next problem, go ahead and use that same concept and try to solve for x. Figure out what x is by using the base angles theorem and the triangle angle sum theorem. That's your hint. What does x equal? Well, if those sides are congruent, we know the opposite angles are congruent. If that's x, then that's x. So you really have an x plus a 30 equals 180. Which means 2x must equal, when you subtract 30 from both those, you get 150. So x equals 75. Alrighty. What does the converse of the isosceles triangle theorem say? Well, if the actual theorem says if the sides are congruent, then the angles are congruent, what is the converse of that? Instead of saying if the sides are congruent, then the angles are congruent, the converse says if two angles of a triangle are congruent, then the opposite sides are congruent. It's a congruent symbol. An example of this would be, if we know those are congruent, then we know these are congruent. That'd be the converse. If we wanted to do a proof, remember, we can use a proof and use CPCTC. So let's go ahead and do that. If we knew those were congruent, I'm going to go over and drop this down at 90 degrees again. And then we have the reflexive property. So those two triangles are congruent by AAS. If the triangles are congruent by AAS, then by CPCTC, we can say that these are congruent by CPCTC. Triangles are congruent, then these are congruent. So once again, we might not actually write out a full proof for it, but we can use our logical skills. And A, then right angles are congruent, A, then S. By AAS, the two triangles are congruent, therefore the parts of the triangles are congruent. Corresponding parts of congruent triangles are congruent. That's what CPCTC stands for. So let's go ahead and look at some of these. So this is giving us information. It's saying, what do you know given this information? If we knew that AE was congruent to CE, then what are the angles that are going to be congruent? We know those ones are congruent. So we know angle EAC must be congruent to ECA. Since the sides are congruent, the angles are congruent. All right, now let's go ahead And look at the next one. If DAE is congruent to DAE, if this one was congruent to DEA, this one, if those angles are congruent, what sides are congruent? Look at the opposite sides of those angles. We would know that DA is congruent to DE. Okay. I think that you guys are getting the hang of this. Hopefully. I don't want to do a million examples. Just basically, if they go over and tell you that the angles are congruent, look at the sides opposite of those angles, and those are going to be congruent. That would be the converse of the theorem. The actual theorem says if you know that the sides are congruent, the angles across are going to be congruent. I think we can skip these ones. If we look down at these application problems, though, let's see. Well, we know that this angle is congruent to this angle. Therefore, those are the sides that are congruent. Those sides are congruent, and that's the base. That doesn't help us at all. So we can now say 28 equals 9x minus 8. Sorry for the bad handwriting. Now we add 8 and add 8. You get 36 equals 9x, so x equals 4. Now on this one, you can see those sides are congruent. Therefore, the angles opposite them must be congruent. 7x plus 5 must equal x plus 47. Minus x, you get 6x, minus 5, you get 42. When you solve that, you get x equals 7. Now this one's tricky because these are the ones that are congruent, so those opposite sides are congruent. But we don't know what this one is. How could we do this? Well, if you knew that this was 60 and this was 60, how many degrees do you have left over? 180 minus 60 minus 60, which is 120, leaves you with 60 degrees. So really, these ones are also congruent, so these opposite sides are congruent. So we can say 2x minus 3 equals 7. 2x equals 10, so x equals 5. All right, so remember, if the angles are congruent, the opposite sides are congruent. If the opposite sides are congruent, then the angles are congruent. Let's look at, I believe this is the last page. Okay. The corollary. Another weird word. Corollary means just like a side note. Corollary to the isosceles triangle theorem. Well, this says if all sides of a triangle are congruent, then what do we know? Let's look at it. Say that is congruent to that, therefore we know those angles are congruent, but it's saying all sides. So now if these are congruent, we know these angles are congruent. So what we end up getting is if all sides of a triangle are congruent, then all angles are congruent. And the converse of that corollary says if all the angles of a triangle are congruent, then all sides are congruent. All right, that explains why if you have an equilateral triangle, then it's also equiangular. And if it's equiangular, then it's equilateral. This is not true for other shapes. For example, you might look and say, well, yes, it is, Mr. Gallagher. Look at a square. All sides are congruent and all angles are right angles. But you could also have all sides congruent, and these ones over here are really big angles, and those ones are really small. So it's not always the case. With triangles, you know if the angles are congruent that the sides are, and if the sides are, the angles are, but not necessarily with other figures. Now we have one last thing here. If the vertex angle of an isosceles triangle is bisected, then the bisector is a, let's take a look. If the vertex angle of an isosceles triangle is bisected, what does it look like it does to the bottom? Sure does look like those are perpendicular, and it also looks like those are congruent. So if the vertex angle of an isosceles triangle is bisected, then the bisector is a perpendicular bisector of the base. Okay. If we wanted to prove that, once again, I'm not going to write out a full proof. We're just going to think through the proof. Here is your triangle. They said it was isosceles. Then they said if we drop this thing down, and we make this an angle bisector, then the bottom is going to be a perpendicular bisector. Let's prove it. Well, we have a side congruent to side, an angle congruent to angle, and then the reflexive property. By SAS, the two triangles are congruent. Therefore, by CPCTC, those must be congruent. So we have the bisector part, but how do we do the perpendicular? Let's think about this. We know the angles are congruent. Angles congruent by CPCTC. We also know that they make a line, so they're 180 degrees together, supplementary. What is the only way that two angles can be congruent and add to be 180? 90 degrees. So we now know that those are 90 degrees. We're not writing out a two-column proof, we're thinking through it. So by SAS, the two triangles are congruent. Therefore, by CPCTC, the sides are congruent, and those are right angles also using CPCTC. All right, now if we wanted to do this, and we want to use this, that's 54 degrees. What is this? Well, we just have to jump through some logical reasoning. If those are congruent, then the base angles are congruent. So if that one's 54, this is also 54. Since this is an angle bisector, we know that that is a perpendicular bisector of the base. So if I draw out one of the triangles, we have a right angle and we have a 54 degrees, and we don't know what that is. How could we do that? Well, we could use the triangle angle sum theorem. 180 minus the 90 degrees leaves us with 90 left over. So those two angles come together to be 90. 54 plus x equals 90. So x equals 36. 36. All right, so for the last one here, it says AB is an angle bisector of the vertex angle. I'm going to draw it. Here's our isosceles triangle. AB is a bisector of the vertex angle. AB is a bisector of the vertex angle of triangle ACD. It intersects the base at B. Got it? If CD, the whole entire thing, was 40, and CB was 2x, then what is x? So this whole thing would be an absolute nightmare if we didn't draw it. If you didn't know what a vertex angle was, if you couldn't draw it, then you'd be in big trouble. Now that we know that this is an angle bisector, we also know that it is a perpendicular bisector of the base. Once again, isosceles triangle, if those are congruent, then we know that we have a perpendicular bisector of the base. So that means that 2x is going to be half of the 40. 2x is going to equal half of the 40, which means that x equals 10. Or you could have doubled it. That would be x as well, and then you could have had the two x's together, which equal 40, and you would still get 10. All right, that's pretty much it. Real quick summary of what we did. We learned the base angle theorem, which says if the sides are congruent, then the angles are congruent, that's the base angles theorem or isosceles triangle theorem. The converse of that says if the angles are congruent, then the sides are congruent. That's the converse. We also learned if you have an isosceles triangle and you have something dropping down here, an angle bisector, then it's going to be a perpendicular bisector of the base. And then we learned that if all the sides are congruent, then all the angles are congruent. And if all the angles are congruent, all the sides are congruent. That was the section. Hopefully it made sense. Come to office hours with questions if you have them, or bring them up in class. Thanks for watching.